Hello everyone and welcome to my screencast on Is Area-Universality Universal Existential R-complete or just UETR-complete? So this is joint work with Michael Dubbins, Linda Kleist and Pavel Zajewski. So this research started when I was in Budapest, and Linda flew over and said, hey, say hello and let's work together. And then Pavel Zajewski, he was also in Budapest, so we decided to work together on this topic. And then later, Michael Gene Dubbins, he came to Berlin, and I said, okay, I come also to Berlin to continue this project. So in this screencast, I want to tell you what the definition and related work to both the concept of area universal, what is area universal, and this weird three symbols called UETR, or Universal Existentiality of the Rails. Then I will briefly present the results that we made, and then conclude with many nice open problems, hopefully. Okay, so let's get started. So what is area universality? So you've given a plane graph as here, and you have certain faces. You could prescribe some areas to these faces. So you could say, I want to have this face to have area 0, this face to have area 3, 1, 12, and so on. And then you ask yourself, can you actually draw it? And that would be a drawing of those assignments, right? However, area universality means for any area assignment, it's possible that we find a drawing. So it's a very strong property of a graph, right? So this graph says here, or I showed here, that for the specific area assignment, there's a drawing, but area universality means for any area assignment, there is a drawing, as in this example. So of course we want to have only positive area assignments, and we also allow 0, but not negative area assignments. So what has been done to this concept of area universality? So a folklore result, as far as I know, is that planar 3 trees are area universal. So what are planar 3 trees? You start with a triangle is a planar 3 tree, and then you take any face, in this case the triangle has only one face, and insert a vertex and connect it to its neighbors in the face. And then you take the next face, you place in a new vertex, and you make edges to the neighbors, and so on and so forth. There are many names for it, so that's why I defined it. You might have heard this under another name. And planar 3 trees are easily seen to be area universal. So as imagine we have some area assignment. So we already drew the outer triangle with the correct area, and now we have to inductively add this vertex. So we don't really know how to connect it, where to place it, but we know the areas of these 3 faces. So what we can do is, we know, because of the lower face, we know that the vertex must be on this line parallel to the lower face, to this lower side, and the same for this left side. And then there only remains one spot where I can put this vertex in order to make the right area for this and the right area for this. And since I drew the outer triangle correctly, this will also have the right area. And then you continue inductively. So it's very easily seen that this big class of graphs, namely planar 3 trees, is area universal, which is a very strong motivation to study the concept, right? I mean, it's kind of pointless to study a concept that doesn't really exist. But there were a few non-trivial results. So Thomason showed in 1992 that plain cubic graphs are area universal. But this paper is very deep, and it has a lot of very long lemmas. So I will not go into this. So note that cubic is as sparse as you can get without having degree 2 vertices, and still it's very hard and technical proof. And then Linda, she showed that one subdivision of any plane graph is also area universal. So if you have the flexibility of making a bend essentially in every edge, then you could. Then you're area universal. Yeah. And on the negative side, Linda showed that Eulerian triangulations are not area universal. So triangulations such that there exist in Eulerian path. So very, very little is known, and this is because it's very hard to study even simple graphs. Somehow this notion is very challenging to study. And then in 2000, or in this year, EuroCG, we asked, is this specific graph area universal? Because we somehow wanted to show that it's even for a single graph non-trivial to do progress there. And yeah, so then this guy Manfred Scheucher, he showed no, it's not possible. And we're quite happy about this. And his proof, it really shows, okay, a given graph, it's not impossible to decide if it's area universal or not, but it's pretty hard. In this case, it was a no instance, which made it much easier. Nevertheless, he needed 3 different area assignments, so different sizes of areas, so 0, 1, and 2. So you couldn't just do 0 and 1, as some people suspected. He needed many cases, and you have to see this example here is symmetric, which helps, and it's tiny. And nevertheless, in order to find a proof, he needed computer assistance. So the point here really was that studying even small graphs is non-trivial. Yes, and yeah, we're glad that Manfred Scheucher could solve this, and we promised him a cup, and he won a cup. Okay, so this is a related work on area universality and what we should know about it. So let's now move to this weird letters. So we start with something which you might be more familiar with, is existential R. So existential R is anything, this is a complexity class, and it's anything that reduces implementation time to this problem called ETR. Okay, so now I've explained this with other letters. So what is ETR? ETR again is called existential theory of the reals, but now we consider a specific computational problem, namely deciding whether there exist real variables such that a formula phi is satisfied by these real variables. So this is where the name comes from. We ask for the existence of real variables and then satisfying a certain formula. And now the question is, what can this formula have? This formula is any well-formed formula which consists of the constant 0, 1, any variables you like. You're allowed to have equations, inequality, arithmetic operations, and logical operations, and or not. So here's an example of what you could ask. So you could ask, for instance, that s squared plus y minus x times z plus 12 equals 5, or it doesn't hold that this is true. So you want to know whether there are real numbers which satisfy this thing, but do not satisfy that thing. And here I was cheating a little bit. So for instance, x squared is not allowed, but this is not a thing we can just replace x squared by x times x. And minus x is also not allowed, but we can replace minus x by x prime, where x prime is just x plus x prime equals 0. So then that would be the negative here. Also 12 must be replaced by something. I haven't placed the old brackets. That would be necessary, so that one might want to add or not. And here's the inequality I put in the wrong way. I've allowed only this way, but it doesn't really matter. Okay, so yeah, so this kind of sentences we can decide, or we asked to decide over the reals. And it's sometimes referred to as the real analog to NP. I like to call it the real analog to NP because here we have a formula and we have real variables. And in NP we have Boolean for variables and Boolean logical formula. Here we have an arithmetic formula. And it's trivially seen that this is more powerful because we don't just have Boolean operators, but also arithmetic operators. So this is truly more, this is more difficult than SAT. And we don't know if it's truly more difficult than satisfiability, but it, it a little bit looks like it. So why is this class existential R important? So first, as I just showed you, it's known to contain NP, and this is kind of trivial, but it's very non-trivial to know that it's contained in P space. So this is not everyone knows this, but you should know. But it's a very long algorithm which developed over decades of research, and it has specific importance to geometry. So let's look at a geometric problem to see this. So this problem that I want to consider is recognition of segment intersection graphs. So there's a following problem. You've given as input a graph, and you want to know whether you can represent this as segment intersection graph. So for each vertex, you would place a segment, and any two adjacent vertices, the corresponding segments here should intersect. So red is intersecting light green, dark green, brown, and you can see red is intersecting light green, dark green, brown. Wonderful. So this would be a true representation of that graph. And then people considered, obviously, the question of whether recognition of segments is contained in NP, and the easy certificate would be, well, just place those segments, right? And that's your witness. But then there was a question, but do we have natural numbers as coordinates? Okay, so you can wiggle a little bit, and you can see you get rational coordinates, and then you can do some scaling, you get natural coordinates or integer coordinates. But then the question is, how large might these coordinates be? And to cite Jirka Matuszak, serious people seriously conjectured that the number of digits can be polynomially bounded, but it cannot. So actually, this simple idea of showing that it's an NP failed. So the integer representation might need 2 to the omega of n bits. This does not mean it's not contained in NP, but it does mean the most simple way that you would want to show it, that does not work. And then later people figured out, oh, actually this problem is existential R-complete. So this kind of innocent looking problem is as hard as any other problem in this complexity class existential R. Okay, and so there are a bunch of these problems which are existential R-complete, and this makes it interesting for us as geometers to study this. So for instance, unit disk intersection graph, same thing. Minimizing the crossing number of a given graph. Recently, the artillery problem was shown to be existential R-complete, which was a big surprise, I guess. Then pseudo-line stretchability, here we have given curves, monotone curves, and we want to just find, can we get the same arrangement with line as a line arrangement? It's not curves, but line arrangement. This is hard. Recognition of visibility graph, meaning can this graph be represented as a visibility graph of points, and then realizing a graph or combinatorial poset as of height 4 as a polytope in R⁴. It's called Steinmetz problem for 4 polytopes. So all these geometric problems are existential R-complete, and this makes it interesting to study or to be this is why we should be aware of this complexity class, because for certain kind of problems it really captures the complexity, and it shows us that a problem is not in NP where maybe we would expect it to be. Okay, so before now we can tell you the result, there's one last slide of definition, so bear with me. So there's this famous polynomial time hierarchy. So we have this complexity class NP and co-NP, which are very well known, and then there's this polynomial time hierarchy that is well known, but maybe not as well. It is called sigma pi 2 and pi 2 p2, and so it's defined as follows. NP, as you know, is defined as does there exist some Boolean variable satisfying some Boolean function, and this is called satisfiability. And then co-NP could be defined as a complement, but you could also say everything that reduced to tautology, which is it true that any Boolean variables that I plug in this as phi satisfy phi. So yeah, it would be co-NP. And now you can play this further. You can say instead of just one quantifier, we have two quantifiers, one universal and one existential. And depending on which order, we have these hierarchy, and we can push this more and more quantifiers, and we get higher levels of hierarchy. But here for us, only interesting the first two levels. So now what I want to do is I want to replace Boolean variables by real variables, and this gives me these new complexity classes. So here we've already seen if for NP we replace Boolean variables by real variables, then we get this complexity class existential R. For co-NP we would get for all R, universal R, and here higher in the hierarchy we would get universal existential R, existential universal R, and universal existential R. So these complexity classes are defined in a canonical way. But as far as I know, apart from these two here, those above have not been studied rigorously. I think Markus Schäfer studied them, but I haven't seen something published by him so far on the subject. So what is our result? So first we have this conjecture that this area-universality is universal existential R-complete. And we believe in this conjecture for the following reason. So the area is somehow universal, can be seen as universal quantified. We want to have a property which is true for area assignment. The vertex placement is existentially quantified. So for every area, we can choose our vertex placements. And then these values that we have, right? So what we vary over, this is real valued by default, right? So we don't say we just allow area 0, 1 and vertex placements 0, 1. No, we say any area assignments we allow and any vertex placement we allow. And sometimes we know these vertices must be placed at irrational numbers. And we don't see how the values could just be reduced to Boolean. So this is the motivation for our conjecture, and we give it anecdotal evidence. So we show that fixed prescribed areas existential R-complete. So this means we are allowed to fix a position of some of vertices, but not all. Area-universality for triples is universal existential R-complete. So here we allow crossings, and there's also some other things, some technicalities that we have to consider, but mainly we allow crossings. And then volume realization is also existential R-complete, and here we go to 1 dimension up, we go to 3 dimensions. So these are our results. I will not show you anything of the proofs, unfortunately, but I want to use the time to give you related and open problems. This is because, so we have this hierarchy, and we don't really have problems here which lies on this level of the hierarchy. So maybe in this workshop, maybe we can motivate this class and make it an interesting class by giving potential problems that might be potentially hard for that class, and you can see if you find these problems interesting. So the first problem that I want to talk about is called universal graph metric, or we call it universal graph metric. The input is again a graph, and we want to give for every reasonable edge weight function, we want to find a realization betting in the Euclidean plane, realizing these edge weights. So here we have given a graph, and we have edge weights. So this weight has this edge has weight 3, this edge has weight 5, and so on. And now the realization would be the following. So here this edge has length 3. In this embedding in the plane, this edge has length 4, and this edge length has by Pythagoras length 5. And yeah, as this is what we want to achieve for any reasonable conditions on these, or for every edge weight function which is reasonable, we want to find an embedding. So for certain this is hard, but is it hard still if we want to have it, if you ask for realizability for any edge weights? Then you would think this is harder, but kind of if you look at this problem, you can notice it's minor closed, and we know minor closed properties can be tested in polynomial time. So here, really the interesting thing about this problem is, instead of having universality over areas, we have universality over all graph metrics. And then the problem, instead of becoming more difficult, it becomes easier. It becomes polynomial time solvable, but it uses this huge machinery of minor closeness. And notice area-universality is not a minor closed property. Okay, so this is not an open problem, but it's a very much related problem that I want you to be aware of, which kind of weakens our conjecture, but yeah, still it shows that our conjecture is kind of on the edge. Another related problem, an open problem, is this of universal guard extension. So here the spirit is that we've given some regions, so here's these two red regions, and we want to be able to find a guarding no matter where guards are placed in the red region. So there's someone, adversary, who places 2 guards in these red regions, and no matter whether he places them or she places them, we should be able to guard this. And here you can see in this polygon, if these 2 positions are used for guarding, then and only one more guard is allowed, then in order for this guard to see this point and this area, it is impossible, because it needs to be left of this area to see or he must be on the left of this line in order to see this point, but then it's impossible to see that. So this is universal guard extension. So this is my first super problem, and it's it's kind of interesting of a problem, right? So this might really happen that we say, okay, well, someone else is doing some guarding, we have to do the rest. Can we always do it no matter how much they mess up? Because maybe they don't do things as we like them. And here's the question is let's take any problem with actions that are complete. If we make this extension version out of it, do we get automatically a universal extension are complete problem? So what I want to say is here, maybe this is not just one open problem, but actually many. Okay, so next open problem, universal guarding. So here we've given as input these disks, and we don't know the exact polygon. Okay, the polygon might look like one of those 2 in gray or any other. We just know that the vertices, each vertex is in one of those disks and then goes along the order of these disks. And then what we want to try to do is we want to still find a guard that no matter how this polygon looks like, this is the brown thing is a guard, it can still guard everything. And here it would be the conjecture or the proposed problem is this hard for this EUTR. So maybe this is hard for, again, the second level of the hierarchy, this problem. And here we have 2 canonical quantifiers, right? An existential quantifier for the guards and a universal quantifier for the position of the polygon. Yeah, why is this problem interesting? Because it gives a solution, or the solution that it gives is robust to imprecision. So now our guards, maybe we need more guards for the stronger condition, but maybe if we did some measurement errors in how the polygon actually look like, then our guarding is robust to this. yeah, so this is why this concept might be preferable to the normal gardening. And again, this dealing with imprecision might lift the complexity of our problem one level higher up in the hierarchy, and it might imply real algebraic connections. But we don't know that. So that would be interesting to look at. The same you could do with domination of unit disks. So here is a unit disk graph intersection graph, and we want to find a dominating set such that even if we move things a little bit, then maybe some of the connections here, some of the dominations are destroyed, but we want that still every disk is dominated. So yeah, again, maybe one level you go higher in the hierarchy, but you might have a more robust concept of domination, which deals with the imprecision that maybe we don't really know if these two disks intersect or not. So here you can see that this blue disk, it might, by a small perturbation, avoid any of these red ones, but maybe not all of them at the same time. So picking all the three red ones might be sufficient to guard this disk here, which you can see here. Okay, okay, same questions. Going one level up in the, do we go one level up in the hierarchy by dealing with imprecision, and do we get real algebraic connections? Then we have a robustness in a different sense. So imprecision means we have imprecision input, but now we want to deal with robustness of the output. So again, I take the art gallery problem as an example. So instead of outputting just the guard positions, maybe we want to output disks here, such that no matter where I place my guards, I can still guard everything. So the idea is, maybe I tell someone, okay, you need to place guards there, but they will not do this very precisely, right? The guards will not stick to their positions all the time. They move around a little bit. Maybe we have cameras which have them, which cannot see, or which have them space that they take, and we cannot have full control of where they place them. So we want to have a solution which is robust to this, meaning even if there is some slight perturbation in the solution in the real world data, it's still a good covering. So that might be a different notion of robustness. We could ask for that. And then, we get two quantifiers. We get an extensional and a universal quantifier. And then the question is, do we go one level up in the hierarchy? Okay, so one of my last open problems is about recognition of heart shapes. Again, this is robustness adding to the output. So the problem usually is for recognition of heart shapes would be we've given a graph and we find a drawing that, or if we find a heart shape representation of it as a heart shape intersection graph. And but now we want to give also some delta, and we want to make sure that whatever representation is given me by the algorithm, that if I wiggle it a little bit, it's still gonna be a valid representation. And again, we have these two quantifiers, so it might be one level higher up in the hierarchy. So here we have a representation, but you can see if I wiggle it a little bit, then no intersections get destroyed. I'm not sure if this is really one level higher up in the hierarchy, but yeah, so if not, then maybe we can find some arguments why this is not the case. So yeah, it's not clear if this is easier or becoming easier or more difficult now, the question. Maybe it becomes easier. So we should really look at this robustness notions. Maybe we get not just better solutions because they're robust, but also we can compute them more easily. That would be nice. And yeah, so my last problem, this was actually communicated to us by Markus Schäfer, is about the Hausdorff distance. So yeah, we have given two quantifier-free formulas, phi and psi, in the first order theory of the reals. And then the question is, whether the Hausdorff distance is 0 or maybe smaller than some given epsilon. And this for us here boils down to, are these two sets the same? And you can see phi could just be this simple equation and psi could be this other simple equation. And if you draw these two sets which satisfy this equation, you see, oh, it's the same, right? So maybe recognizing if two formulas give the same thing might be harder than just existential hard. Yeah, so that's a very interesting question, I find. Okay, and yeah, thank you for your attention.